Okay, let's start. So today's class is on section 12.3, which is erratic motion. We'll be looking at graphs of velocity versus time, acceleration versus time, velocity versus distance, and from those graphs, we'll be solving for distance covered, acceleration, velocity, and so on. Okay, so a brief overview before we start solving problems. Okay, let's look at acceleration is dv dt. Okay, so in order to understand this expression, let's look at a plot of velocity versus time. Okay, so given the velocity, you can actually draw the velocity as a function of time, and if you want to find the acceleration at any point of time, let's say at this point, then all you need to do is get the slope at this point. The slope is basically the acceleration, which is the rate of change of velocity with respect to time. Okay, so in this case, we're interested in the velocity at, acceleration at t equals t1, and you can find that from the slope. Let's look at this formula in a different way. Let's try to, well, I'll multiply both sides by dt and then take the integral. So a dt is dv, so I can write integral dv is integral a dt. I'm just going to put some limits of integration, v1, v2, t1, t2. So the left hand side is trivial to integrate. It's just v2 minus v1. However, the right hand side, I cannot integrate it unless I know an expression for the acceleration. So if acceleration was t, then that answer would be different from acceleration as t squared, t cubed, and so on. So I'll keep it as it is. So the other way to think about this particular formula is a dt happens to be the area under the acceleration time plot. So if you draw a plot of acceleration versus time, and that can be, let's say, something like this. Let's say that this is t1 and t2. Then this area here is integral t1 t2 a dt, or area under AT graph from time t1 to t2. So what we've done last time is I gave you a formula for acceleration, and using that formula you were able to compute this integral, and because of that you were able to find the rate of change of velocity. What this is saying is that you can do it another way. Instead of trying to integrate this, you can draw a plot of acceleration versus time and then look at the area under the curve. And that is actually sometimes very simple because we can find the area of shapes. So we'll see that problems where the area is basically the area of a square, area of a trapezoid, area of a triangle, and so on. And that's really easy to think and interpret. So this is another way of solving the same problem. Okay, let's do another. Let's look at the other formula before we start solving problems. The other formula has to do with velocity as a function of distance. So this is looking at a equals dv dt acceleration. Look at the other formula we talked about yesterday or day before yesterday, and that is v equals ds dt. Okay, this has exactly the same interpretation as the previous one. If you want to interpret the velocity, what you do is look at a plot of the distance as a function of time, the slope is ds dt. In this case, it's at time t1. So that is the velocity. So the slope of the st curve at any point is the velocity, just like a is dv dt. The other way to interpret this, similar to the previous case, is you multiply both sides by dt and take the integral. So that would give me ds. Integral ds is integral v dt, and I'm going to use limits s1, s2, v1, v2. So I can find the left hand side. It's simply s2 minus s1 However, I'll keep the integral in place because unless I know what the velocity is, I cannot evaluate this integral. Right? Unless I know v, a function for v, I'm not able to do that. So I'll keep it as it is. It turns out that v dt is the area under the vt plot. So if I draw the velocity time plot, which is the same plot I drew previously, then this thing here is t1 t2 v dt, or area under vt plot between t1 and t2. So again, if you knew velocity, you can find the change in displacement. S2 minus S1 is displacement. Or if you did not have that information, if you knew a plot, if you drew a plot of VT, then you can basically find this by finding the area under the plot. Okay, is that clear? Okay, is that clear? So what we'll do essentially is we'll take these two things and start solving some problems. Okay. Okay, so the velocity time graph of a car is shown below. It's not so much to scale, it's poorly drawn. It doesn't look like it's possible. There, find the total distance traveled and draw the acceleration time graph. Okay. So we do not have a closed form expression for the velocity. We're only given a graph of the velocity versus time. So this is where you will use the things which I just talked about. So we know that v is ds dt. So ds from s1 to s2 is integral v dt. Time goes from t1 to t2. So this is S2 minus S1 is T2 T1 VDT. So the total distance covered, so assuming that the total distance covered is actually S2 minus S1, right? S1 is the distance, well, it depends on what 1 and 2 is. In this case, I'm going to assume take 1 to be here, this is T1, and this is T2. Okay, so the distance covered from T1 to T2 is going to be, well, it's going to be, if you think of the car or whatever object starts at T1, then the distance covered is going to be the displacement, which is S2 minus S1. So we want to find total distance covered or traveled is area under VT plot from T1, which is equal to 0, to T2, which is 80. Okay, so this is the total distance covered. This is the area under the plot. Okay, so this is where you got to remind yourself of area of shapes. So in this case, we have two shapes. We have a square, not a square, sorry, it's a rectangle. It looks like a square. It's not a square because and it's made up of a triangle. So the area of a triangle, what's the area of the, area of the rectangle, what's the area of the rectangle? Half base times, base times height, right? The base is 40 and the height is 10. So it's 40 times 10. This is this part. And then what's the area of the triangle? It's half base times height, or base times height divided by 2. So it's half base, which is this distance, it's 40, times the height, which is this, it's 10. So what's that? It's 400 plus 200, 600. Okay, is that clear? Okay, the next question is draw the acceleration time plot or acceleration time graph. Okay, so the acceleration is the rate of change of velocity. This is v time a time. So in order to draw the acceleration time plot, we need to look at what, let me just draw it this way so it's much easier. Just below this. Okay, so all I need to do is look at the slope of the VT plot, right? Slope of the VT plot, and that should give you the acceleration. So the slope is, you can see that it's a straight line parallel to the time axis, and then it slopes down. So what's the acceleration here? It's zero because the rate of change of velocity is zero. dv is zero, right? Velocity does not change. So that's going to be zero. However, for the next second part, it's not zero. The slope here is not zero. So you're going to know how to find the slope of a line. Do you remember how to find the slope? You need the coordinates of at least 2 points to find the slope. In this case, I think, well, this one, you know, it's 80, comma 0. 80 is on the x-axis, the time axis, 0 is on the y-axis, and this point is 40, comma 10. So I'll write it down here. 40, comma 10, and this is 80, comma 0. Okay, so I'm going to use this formula here to find the slope. I need 2 points, as I said, this point and this point. So I need to find the difference between the y coordinates. So that's going to be 10 and 0. So 10 minus 0 divided by the change in y coordinates. So it's 40 and 80. So 40 minus 80. Okay, now you're going to be careful. You're going to take the same points. If you take, so 40 comma 10 is 1 point, so 40 and 10 appears first, and 80 0 is the second, so they don't just swap it. It's because you like it. It's because 80 is greater than 40, don't swap it. You've got to take in the same way, otherwise you get the wrong sign. So when you do this, you get minus, I think, 0.25. The minus has a meaning. The minus means that the slope is negative, and the slope of that line is negative. A positive slope is when it would be, if the line was this way, it would be positive slope. If it's this way, it's negative slope. Okay, so from here to here, the slope is constant and it is negative, like so. And this coordinate here is negative 0.25, what we just found here. So that is the acceleration time plot. Any questions? Okay, this is the only question. I'll let you go after this. Just 2 questions today. So a jet car is traveling at a velocity of 10 meters per second when it is subjected to the acceleration profile shown below. Okay, so acceleration time plot. Find the car's maximum velocity and find t prime here when the car comes to stop. They're given that when time t is 0, s is 0. Actually, also given that v is 10 meters per second, right? Right here. So initially the car is traveling with a speed of 10 meters per second. And then it's subjected to acceleration. So how can you accelerate? Well, you just press on the gas pedal. That's how you accelerate. So you get acceleration. And then if you brake, you get a deceleration. So this is deceleration, so it's negative acceleration. So what's going on here is there's acceleration, there's deceleration. So if you decelerate, if you press the brake long enough, then clearly the car is going to come to a stop, and you have to find the time when it comes to stop. Okay, so the first question is find the maximum velocity. Okay, where first of all you got to figure out where in this particular plot does it achieve maximum velocity. It starts off with 10 meters per second. This is not, by the way, this is not a velocity plot. This is an acceleration plot. Okay, you're given that the acceleration here is 10 meters per second, and then some point of time it hits a maximum velocity. You got to find where that time is. Once you find that time, you can then evaluate what the maximum velocity is. So, can you guess where the maximum velocity might be on this plot? At what time? At 15 seconds. Any other guesses? Okay, so it has to be 15 seconds because what's going on is this person is pressing the brake, sorry, the accelerator or the stepping on the gas pedal. He's accelerating. So when you keep accelerating, your car will keep speeding up. The moment the person presses the brake, which is here, it's going to start slowing down. So clearly, the transition from stepping on the gas pedal to braking is going to be the point at which the car achieves maximum velocity. So it's going to be at 15 seconds. So the car is accelerating from 0 to 15 seconds and decelerating from 15 seconds onwards. Thus, max velocity will occur at time t is 15 seconds. Okay, now that we've figured that out, let's try to find the velocity. So if we're given the acceleration plot and we're told to find the velocity, then we can start thinking of what's the formula which relates acceleration to velocity. The formula is a equals dv dt. And if you want to find the velocity from the acceleration plot, we need to take the integral, right? So dv is integral a dt. In this case, the initial velocity is 10 at t equals 0. We are interested in finding the velocity at 15. So I'll write it at v max is at 15. The initial time is 0. The final time is 15. Okay. So we know that a dt, or the integral a dt, is the area under the acceleration time plot, and that's precisely what we have. We have an acceleration time plot. So if we can find the area under the plot from 0 to 15, then we would have computed a dt. So what's that area? What's the area under the plot? It's a rectangle. So the area is base times height. The base is 15. The height is 6. So that comes out to be, is it 90? Okay. So we have V max minus 10, right? Don't forget this, equals 90. That means the maximum velocity is 100 meters per second. Okay, is that clear? Okay, the next question is find the time t prime when the car comes to a stop. So because the car, so right now at 15, the speed of the car is 100 meters per second. Okay, so after from 15 to t prime, it's decelerating. So when you decelerate or step on the brake, it's going to decelerate, eventually come to stop. So we need to find the time at which it comes to a stop. So if you want to find, in this case, we're given the velocity at t prime is 0, and we need to find the time. we can again use the same formula which relates acceleration velocity, because we have the acceleration plot and we know something about the velocity at 15 and we know something about the velocity at t prime. So I'm going to use the same formula except change the limits. So integral dv equals a dt, except that I'm going to go from 15 to t prime. So the velocity at 15 seconds is 100 meters per second. It's going to be 0 here, right? Because the car comes to a stop. The acceleration at, well, the time at the first instance is 15, and I do not know what the time is at t prime. I need to find that. That's the unknown. So this gives me 0 minus 100 for the left hand side equals the area under the, so it's going to be this area now. So that is also a rectangle, and the area is half base times height. Sorry, base times height, my bad. Base is t prime minus 15, and the height is, well, it's minus 4. The area is actually negative. So t prime is going to be, let's say, 20 or whatever. It's greater than 15 times 4 is going to be negative 4 is going to be a negative number, and it's negative because it's below the AT plot. It's on the negative y-axis. Okay, so this gives me minus 100 equals minus 4 times t prime minus 15. So this is 25. And the negative sign cancels, so I get t prime is equal to 40 seconds. Okay. Any questions? Okay, let me just hint at one thing which I think you might need for your homework, and then let you go. Which is, I did not talk about another equation, but you might have problems on that. So the equation which you want to understand is v dv ds is a. So v dv is a ds. So if you take the integral of this from v1 to v2, s1 to s2, then the way to interpret this is, if you look at the acceleration s plot, okay, this is acceleration versus displacement, some weird curve, then s1, s2, this thing here is S1, S2A ds. Okay, and you can write this down as v2 square. I need to integrate this first, so it's v dv is v square divided by 2, and put the limit. So v2 square minus v1 square divided by 2 equals S1, S2A ds. So if you're given the acceleration displacement plot, then you can actually find the rate of change of, well, it's not really velocities, but velocity squared in this format equals ADS. Okay, so you can find the area. Again, there'll be simple shapes, squares, rectangles, triangles, and trapezoids. You can find the area. Okay, so I'll see you on Friday. Please ensure that you get your iClicker, or you have a smartphone or a computer in order to log your answers.